All right, so welcome everyone to this week's edition of the One World seminar in machine learning. And we're very happy to have Nik Nuesken from the University of Potsdam. And Nik just told me that he's very happy to take questions during the talk. So if you have any questions, just post them in the chat and I can ask them to Nik, or you can also just unmute yourself and ask them directly. That's also fine. And then usually we also have a bit of a discussion afterwards, so you're welcome to stay after the talk as well a little bit longer. So Nik will tell us today about the Stein geometry in machine learning. And Nik, you have the screen. Welcome.
Thank you very much, Franka, for the nice introduction and for the organization and for the invitation, of course. Okay. Yeah, so first of all, this is joint work with Andrew Duncan and Szpruch, and more recently, Renger from the Weierstrass Institute in Berlin. All right, and yeah, I thought I would start the talk. Is it actually working? Yeah, okay. I thought I would start the talk with a motivational example, right? So you can think that this is, for instance, the sky, and there are stars or UFOs, right? And now imagine the picture is somehow cloudy or there is noise over it. And I don't know if you can still see it on your screens, but the spots are still very barely visible. And the task might be to find them back, right? And one of the type of algorithms that I want to talk about today, and that I think are very interesting, are based on interacting particle systems. So imagine there's an ensemble of particles on the picture, right, like this. And they are meant to find these stars. So there's going to be some dynamics, some artificial or algorithmic time in which the particle system evolves, right? So I have like a small video. So you can see that, in fact, the particles do manage to find the spots in the picture. And yeah, some also got a little bit distracted, right? So this is the general type of algorithm or dynamics that I'd like to talk about. And the general question is how to approximate probability measures, right? So you can think of this picture here on the right as the target probability measure. So think of the cloud of particles as a probability measure. And there is an initial condition and there is a final condition or a target. And this problem of approximating probability measures is ubiquitous, let's say, in machine learning and statistics, because in the paradigm of Bayesian inference, really probability measures are used for everything. So all the inferences and the reasoning is based on probability measures that describe beliefs about hidden variables. So for instance, the mean of the probability measure could be an estimate, and then the spread of the probability measure could serve for uncertainty quantification, right? And so really what I'd like to talk about is like how we can actually engineer this transition, right? So we go from this initial condition to this final condition to this target. And the question is, of course, maybe how to first set up such a dynamic system, how to analyze it, like what are maybe convergence rates and so on, right? And so in this talk, I'd like to give an overview of 3 different approaches towards this. So first of all, so there's gradient flows, optimal transport, and Markov processes, and each of them will lead to a slightly different type of algorithm. Gradient flows, the idea is you think of this probability distribution as a point in a manifold, right? Is there already a question or no? So you can think of these probability measures that evolve in time as a point in a manifold. So think of this wobbly surface here as a manifold. This point may be evolving inside this manifold, and it is guided by some sort of let's say, loss functional. So it tries to find the minimum, and the target measure will be at the minimum of this functional. So this is the first approach. The second approach would be with optimal transport. I don't have a picture for this, but the idea is that sort of there's a coupling between the initial condition and the final condition, and we're trying to transport the initial condition to the target. Right? And the third approach is based on Markov processes. So you can think that maybe the picture here on the left shows a non-equilibrium situation, and the picture on the right shows an equilibrium situation, and the cloud of particles converges towards the equilibrium. Right? So these are three different approaches, will lead to different algorithms, but these algorithms that I would like to discuss are actually quite similar, and they are sort of linked together through what I call today the Stein geometry. Okay, so let's start with the gradient flow type of algorithm. So this has been introduced now 5 years ago in an amazing paper by Liu and Wang. They introduced this algorithm, Stein variational gradient descent, or SVGD. And this target, so this was the picture on the right, we write it as e to the minus v, where v is a potential. So think of v as like a landscape, and it has valleys. And where the valleys are particularly deep, there is a lot of probability mass in the valley. So yeah, let's say we can describe this measure like this. And then Liu and Wang proposed an ODE of this form. So don't worry for the moment about the k. The k is some sort of interaction, right? So the xi are the particles, and then there is an interaction kernel. And yeah, there are two different terms. One that is related to the potential gradient. So this goes down the valley, so to regions of higher probability mass. And then there's also some repulsion term, because we actually, if it wasn't here, then all the particles would end up in the same spot, right? Okay, and yeah, why is this useful? There are two important facts about this system, coupled system of ODEs. So first of all, so if you look at the, let's say, of the joint positions of the particles in the combined state space, then under some conditions on the potential v, of course, and on the kernel k, then this will converge towards a fixed point. And this fixed point is the one that I showed you in the beginning. And so then these fixed points, they will recover. Oh, this is a mistake here. This is not infinity. This is supposed to be pi. Okay, so this is supposed to say that this empirical measure associated to the particle system, as both t and so the time and the number of particles go to infinity, this will approach the target measure of interest. Okay, so the next question is maybe how this was constructed, or how we could think of this, right? And this was described nicely in a paper by Liu 2017. Now, it was, of course, also in the background of the original paper, and I did some follow-up, and we did some follow-up work on this as well. And a good way to think about it is like this. So we look at the empirical measure associated to the ODE system, and just see what kind of PDEs it is supposed to satisfy. So this empirical measure satisfies weakly this Fokker-Planck equation in so I wrote Fokker-Planck equation, but it's not actually the usual Fokker-Planck equation, because there's this operator tk rho here, which is a convolution type operator. So convolution against the kernel k and against the measure. Yeah. And experts who know about the Fokker-Planck equation as investigated by Otto will recognize the Fokker-Planck equation if you just throw out this integral operator. So now with this integral operator in place, that's a PDE, a non-local PDE, which involves an integral. Okay. And a good way to think about this PDE is to write it in this form. Of course, this needs interpreting, but this means that if you think of this rho T, as I said before in the introduction, it's a point in a manifold. Then we can think of this dynamics as a gradient flow dynamics of some function, namely the KL divergence, so down here, and with respect to a certain geometrical structure, right? So this KL divergence, this is the relative entropy. This is a certain time of discrepancy between rho and pi, right? And it is always non-negative. So you can really think of this KL to look a little bit like this. Parabola. Okay, then next there has to be some sort of gradient operation here, right? The gradient operation is connected to a certain distance on the set of probability measures or distributions. So of course, like intuitively speaking, you can maybe think that derivatives, you take the change of the function over the change of the distance, and so that's why the derivative will depend on the distance. And what kind of distance do we have here, right? So this is supposed to be a distance between two probability measures, mu0 and mu1. And it is we could call this a transport type distance, right? Because it is an infimum over mu and v. And so this means that the way to look at it is dk is the distance between mu0 and mu1 as the shortest connecting curve between mu0 and mu1, when the length of these curves is measured like this. So this continuity equation, this means that the vector field v drives the measure mu. So in the sense of an ODE, when you have an ODE and it is driven by a vector field v, then the corresponding law will follow this continuity equation. And the length of a curve connecting mu0 and mu1 is then sort of by definition given by this integral. So we measure the length or the norm of the driving vector field in a specific space, which I'll address on the next slide. And so this means that infinitesimally speaking, the length of the curve is given by the norm of the driving vector field. Okay, so of course I haven't introduced this space yet. And so I will do this now. Yeah, so this space is related to this kernel function k. And okay, it's the reproducing kernel Hilbert space, or it's the reproducing kernel space to the D. So reproducing kernel Hilbert spaces, at least originally, are function spaces, and then we take the D's power to end up with vector fields. And they are constructed like this. So first of all, there is a pretty stringent condition on the kernel K, namely, so this interaction kernel in this dynamics that we were looking at has to be positive definite. And this means that matrices that you can form in this way have to be positive semi-definite. So a good way of thinking about these kernels is that this is some sort of infinite dimensional positive definite matrix, let's say, right, where you can sort of vary the number of arguments and so on. And one of the main examples is the Gaussian kernels. So this is definitely the most used, and everybody knows what it looks like. And then starting from this, we can think what these functions in the reproducing kernel Hilbert space look like. Namely, they are built together from these basic building blocks where you fix one of the arguments. So this means in this case for the Gaussian kernel that you shift the kernel around like this, and then you can scale it up and some such Gaussian bumps together and you get a function like this. And yeah, from these bumps and scalars, you can then define a norm. It's not so important, so it's not so easy to understand this if you haven't seen this before, but for the analysts, it's good to think that this reproducing kernel space is a Hilbert space inside of A2 under certain conditions, and the norm is quite strong. So typically this is a Sobolev space of quite high order, depending on the dimension. Okay. Yeah. So this is really what is there here. And of course, this looks very familiar to many people because this looks like the Wasserstein-Benamou-Brenier formulation. And I'd like to explain this a little bit. So if in this definition that we just had, so this here below, we exchange the reproducing kernel Hilbert space norm by the A2 norm, then we get here the Wasserstein distance between the measures. So this is the Benamou-Brenier formulation, which has the same interpretation as I explained before, only that the norm of the driving vector field is now exchanged, right? And the brilliant insight by Benamou-Brenier was that this in fact equals the usual formulation of the Wasserstein distance in terms of couplings between mu0 and mu1, where you look for the coupling which minimizes some cost. Okay, so if you do this, then actually not so much changes from the story that I had before. So I said that SVGD performed a gradient flow, minimizing the KL divergence with respect to some gradient structure. And if you just replace the norm here, then you get a different distance on the space of probability distributions, and you hence get a different gradient flow structure here. And the dynamics associated to this is well known. So it's this Langevin dynamics, which has similar features to this SVGD. So it has similar features, some things are different. For instance, the SVGD dynamics is an interacting system and a deterministic system. This is a system for one particle, but it's random, right? So there's a diffusion, but you can still recognize two ingredients. So if you recall, the SVGD dynamics also had a term that had a potential gradient and one term that led to some repulsion of the particles. And here the repulsion of the particles is replaced by diffusion terms. So on the level of the measure, this has a similar effect, right? Because the diffusion term will actually lead to some spreading out of the measure. Okay, and this was famously noted by Jordan Kinderlehrer and Otto. So they noted that this dynamics or the corresponding PDE, such as here, can in fact be interpreted as a gradient flow of the relative entropy with respect to the Wasserstein metric. Okay. Okay, now where can we go from here? Actually, I'm really fast. Okay, so are there questions?
I have one question.
Yes.
So, so the Benamou-Brenier formula has a linear dependence on mu t inside it.
Yeah.
And your version of the formal version of the Stein variational, yeah, that one, it has the same row in front of the t inside the divergence. I'm trying to find that one back in your reproducing kernel Hilbert space. Is it there?
So exactly, the reproducing kernel space does not depend on the measure. So
okay. So then what you're saying is that this row doesn't, no, because then I mean then I would. Okay. Okay.
So one way of, so it's, I mean, this is a very good observation, right? So this norm does not depend on rho. Yeah. And but if you replace here, for instance, mu times v equal to w, for instance, right? Then here you get v over mu, right? As they sometimes do, because then this equation will be linear, but then you get the dependence here after all.
Okay.
Yeah. So it's, I mean, it looks, so the first thing that I thought about is that this kind of looks flat, but it isn't flat in the end, because this dependence is in fact nonlinear.
Okay, thanks.
Okay. Thank you. Yeah, so what I'd like to discuss next are geodesic equations. So, or maybe one comment about this. I said that this is joined together by the Stein geometry. So when I say Stein geometry, it's really this object, so which is sort of at the heart of all this, is the distance on the space of probability measures, right? And so this in some sense defines the geometry. And what is interesting about distances of this form is because they are defined in terms of the shortest length of connecting curves. It's like a geodesic on a Riemannian manifold. So, there can be a lot of developments in this direction. So you can then define a Riemannian structure related to this that reproduces this as the corresponding geodesic distance, at least formally, and define tangent spaces and cotangent spaces and compute curvature and things like this. Now, what I would like to show you here is geodesic equations. So you can associate it to these geometrical notions that come from this distance. We can think of equations for geodesics. So in finite dimension, or just on a usual manifold, if you have 2 points and the space is somehow curved, how can you compute the connecting curve? Right, and this is the same question that you can ask here. So we're looking for a curve of probability measures that connects these two measures, right? These can in fact be computed by looking at formal optimality conditions for this minimization problem. Yeah, this has been done for the Langevin case. The standard geodesics for the Wasserstein case are given as so, where you can see that there's the continuity equation again, and this is a type of HGB equation, which, so you recognize that there's this quadratic term in the gradient, which makes it a control equation, and this is to be expected because geodesics have to be controlled in a certain way to reach their endpoint, right? And then in joint work with Andrew Duncan and Szpruch, we developed the corresponding geodesic equations for the Stein geometry. Now you see that there is this integral convolution operator T appearing here and here. And furthermore, these equations are coupled. So now this mu appears here and it also appears here in the first equation. Note that here these equations are really uncoupled. So this equation does not depend on mu, on the measure. And the fact that these equations are coupled is due to the fact that the particle system is in fact interacting. Right? Recall that the diffusion that I showed, the overdamped Langevin dynamics, just comprised one particle. Okay. Now, why is it interesting to look at these geodesic equations? I just want to give a hint. Yes, sure.
On the previous slide, have you also shown existence of solutions for the geodesic equations?
No, I haven't. So these are formal calculations. In particular, these geodesic equations. I've got some follow-up work where there's actually rigorous mathematics on a sort of different, like using some different techniques, yeah. But it's not so easy because this operator will turn out to be compact, right, because of the integrals. So this is essentially an integral operator, in spite of the derivatives, but there's the integral operator, and this will make this operator compact. And so, for instance, given dt mu, this is difficult to solve, right? If this is a compact operator, this is then hard to invert, let's say. So my hunch is that they're not generally well posed or so. But it's an interesting question. Yeah.
Do you have existence of, I mean, forgetting about the equations, do you have existence of geodesic minimizing curves?
I'm not sure. So I should have said this maybe more clearly in this in the beginning, right? Parts of this work are quite formal, so these are formal optimality conditions. Yeah.
I mean, you said that the okay, no, we'll talk about it later.
Yeah. Okay.
Yeah. Thanks.
Thank you. Okay. So this is just a sort of an advertisement slide, right, for this work, because so we were interested in these geodesic equations because when you have these geodesic equations, you can hope to say something about the convergence of the gradient flow dynamics. Namely, so intuitively speaking, if this if the valley is more curved, if it's more convex, then the convergence to the minimum will be faster, right? And the way to formalize this, or to say this rigorously, is to have the right notion of convexity. And the right notion of convexity is to look at the second derivative along geodesics. So in the usual case, you have to look along at geodesics along straight lines, but straight lines in this geometry are geodesics. So it's then possible using these equations to compute these terms and try to say something about this rate. But I will not say more here because I will say more later about this. Okay. But this is a general idea in this type of field and of gradient flows, how you could go about understanding some of the properties of this. And maybe I haven't stressed this enough, but the convergence speed is really interesting for the applications, because if it converges faster, then the algorithm will be more efficient. Yes, okay. So this is another slide, this is, which is a little bit very formal, but this can actually be made rigorous. But I'd like to just explain some of the ideas behind this. So I'm switching gears now. This talk until here was about the gradient flow. So this was, let's say, algorithm 1, the original SVGD algorithm. And now there is a different idea of approaching the problem of approximating probability measures. So we can just try and solve some sort of optimal transport problem. So let's say transporting one measure to the other measure on a time interval from 0 to 1. This has the appealing feature that we don't have to wait until time goes to infinity, right? So there will be convergence if this works in finite time until t equals 1. And this holds the promise of really drastically reducing the computational cost. So now, so this is a different approach, will lead to different algorithms. But yeah, what is of course the problem straight away is that, so for instance, we could look at this formulation over here and try to solve it. But this is computationally very demanding, right? Because you would need to find this infimum. And in fact, the optimizers, at least formally, are characterized by these geodesic equations, right? So by a system of coupled PDEs, which is very unappealing computationally. Okay. Now, one idea is that this optimal transport problem actually becomes a lot easier if the two measures mu0 and mu1 are in fact close to each other. And so you can think of the first geodesic equation in this form. So I'll just put the dt mu on the other side. And one way of reading this equation is now that this is sort of a small perturbation of the measure mu. And we think, so you can, or I encourage you to read this equation in this form, that we have some measure mu given, and then there is some perturbation of this measure mu. So I'm noting this here in a kind of sloppy way like this, but this slide in fact can be made rigorous, but I'm not showing it. And then we are trying to find this function psi. So this is related to Franca's question before, right? So this is given mu and dt mu, can we find this psi? And this looks a little bit like an elliptic equation, so up to this integral operator here. And this can in fact be approximated in practice. So because you do integration by parts here and so on, and then this will be an integral equation, and you can approximate the integral by a matrix multiplication. And this is what happens here. So maybe I should explain the intermediate steps before. So I'm going to explain this. The idea of doing this, the idea how to do this is we fix a curve that connects the initial probability measure that we had and the final probability measure, so the target, by an interpolating curve. This can be usually done in this way, and this is because in Bayesian inference, this is a very typical way of writing the target measure. So there is the prior, which encodes prior information, and then there will be the likelihood. And so this can be read as Bayes' theorem, in fact. And the time t goes from 0 to 1. Yeah, and again, this is a curve connecting u0 and u1. And then, again, intuitively speaking, we can think of performing these infinitesimal optimal transport maps on a discretization of this interval. So if we discretize this interval, this is only for intuition, right? This can be in fact made a little bit more precise. But then for any, so between these measures mu ti and mu ti plus 1 that arise through this interpolation, if you discretize the time interval, then you can go about solving this equation numerically. And so this is then what will come out in the end. This is the second equation is a discretized version of this equation. So as I said, this will become an integral operator, and this corresponds to this matrix here. And you can solve for this psi. Yeah, and what is interesting is that this in fact looks quite the same as the original SVGD algorithm, with the important feature that there are now the weights, and that time goes from 0 to 1, and not from 0 to infinity. Okay, yeah. This is my slide on this. This is some also advertisement for this work, which I'm currently finishing. It will be on archive late next week or early the week after. Really, because there's a deadline. Okay. Yeah, so this is the second approach connecting, so for Bayesian inference, approximating probability distributions using the Stein geometry, but yeah, constructing a slightly different interacting particle system. Now, I'd like to discuss the third approach, which is, which you can see here. So as you remember, this was the deterministic dynamics that we had before. And we can try and inject some extra noise into the dynamics. So why is this good? Well, let's first describe its form, right? So this extra noise, there's some bounding motions, and there is a matrix multiplying it, and this matrix is built from the kernel. So that's, yeah. And this extra noise has been constructed in a very special way, namely so that the target measure, pi, if you tensorize it, will be invariant, and in fact, under certain conditions on the potential V, will be ergodic for this interacting dynamics. So what does this mean? We look at these interacting particles on the joint space, and they will converge for a long time towards this measure. Or in other words, if we look at an ergodic average like this, then we will get here. Okay, and for computational purposes and also for theoretical purposes, it is interesting to note that the limit as n goes to infinity is not needed, right? So you can compute the measure, the target measure pi, if you fix n. So n can be, for instance, 10. And if you let t go to infinity, then you will recover the pi on the extended space, but its marginal will give back the targets that we were interested in the first place. So this is interesting, of course, from a computational perspective, because then the number of particles that we might use can be smaller, but also from a theoretical perspective, because this will, as I will show, help us to understand the finite particle effects in the deterministic system. Yeah. So the next observation is that this Fokker-Planck equation that we had before, that looked like the ordinary Fokker-Planck equation, however, including this integral operator t, is in fact the mean field limit for the empirical measure associated to this SDE system. So what this is supposed to tell you is that the extra noise that is injected here becomes negligible, right? Because the mean field limit for the stochastic and the deterministic system will in fact be the same. Note that actually the behavior of these two systems is vastly different, right? So in particular, there is an interesting, let's say, non-commutativity of limits that I'd really like to understand a little bit better. So for instance, if you think first about the system, about the deterministic system without the noise, then I said that it will converge towards a fixed point, right? So this means every particle goes to its final position in the picture, right, that we had in the beginning and stay there. And this is, of course, kind of the idea behind this algorithm, that not every particle has to explore the whole space to find the target measure, but they can collaborate in such a way that one particle maybe goes to the right and the other particle goes to the left. So this was, let's say, first taking n to infinity and then looking at t goes to infinity, right? If we do the other limit, so if we take t to infinity first, then we are in this ergodic state, which is a product state, which means that the empirical measure is distributed according to this product measure. And this means that statistically every particle in fact visits all the state space. And in fact, this might be unwanted computationally, because if you remember this target measure that we had in the beginning, which had multiple modes, then it means that one particle has to jump through the modes, and this might be quite difficult to do because there are regions of low probability. Okay. So I think this is quite interesting to understand, and together with Nik Renger, we made some advances on these connections. So one interesting question is, of course, how fast is this mean field limit, right? And in particular, can we maybe choose a kernel K such that this limit is especially fast? Because this K, this kernel function is specified by the user who runs the algorithm, and so in fact it should be chosen in such a way such that this limit occurs in a speedy fashion. Okay, so what we did
can I ask a question?
Yes, sure.
So for the previous thing, SVGD with noise, so it seems there is a trade-off between M being large or being small, right? Because if it's very large, then it's essentially just deterministic. And so, but then when it's very small, then it's far away from the mean field. So in practice, how would you choose N for this stochastic SVGD?
Good question. I'm really not sure. So there are a lot of trade-offs here. So computationally, one trade-off is that it's quite unpleasant to compute the matrix square root computationally. And then also this effect that I mentioned that in fact, we've got this as the target, right? For the stochastic system is, I think, not great, especially in multimodal situations. How large one should choose the N is really an open question, I think. In fact,
and this coupling is needed to get to that invariant measure, right? So it's not just for reducing the asymptotic variance or something like that.
You mean this noise structure?
Right. So can one choose a different structure to get the same invariant measure?
I think no, but I'm a little bit unsure, but I would be surprised. Yeah, so I wrote down, I mean, you can write down, of course, the stationary Fokker-Planck equation and things like that.
Yeah. The one that you wrote down is just the fluctuation dissipation rule, right? So because
yes, exactly. Yeah, it's the fluctuation dissipation. So there are these works where they sort of classify all the, given an invariant measure, classify all the possible dynamics, right? So in fact, if you want a reversible diffusion, this is unique. But so what I'm a little bit unsure about is that here you fix the product measure, right? But let's say you only fix the marginals, which would be enough for, in practice, then there's quite a lot of choice, right? And then I'm a little bit unsure. Yeah.
Okay, thanks.
Thank you for the question. Okay. So yeah, so this is maybe related to this question. So we were interested in these asymptotics, right? And Mikil is an expert on large deviation principles. And so recall the statement that I made here, that the mean field limit associated to this interacting particle system is in fact the same equation, right? So we can think of making this statement in a little bit more quantitative way. This is the more quantitative way of making the statement. So we look at the empirical measure associated to the SDE, which is a random measure, because there's noise in the system, and yeah. And this satisfies a so-called large deviation principle. So this random empirical measure depends on n, and when n goes to infinity, we are expected to get back the solution to the original Stein Fokker-Planck equation, right, which is deterministic. So as a random object, this is supposed as n goes to infinity to converge to something deterministic. And the way it converges is described like this, where there is a function in here which depends on this rho. So you should read this equation as rho as the free variable. And let's say there's two possibilities. Either rho satisfies the PDE or rho doesn't satisfy the PDE. So if rho satisfies the PDE, this is the PDE, then this function will be 0. And so the probability here will be will be 1. So, and otherwise, if there is a deviation from the PDE, then these fluctuations away from this mean field limit will be exactly described, or up to up to sub-exponential terms will be described by this functional here. Yeah, and what is especially, so what is interesting about it is that this norm here, we need to talk about this norm. This is in fact the tangent norm in the Stein geometry. So I showed you the distance between probability measures that was induced by the reproducing kernel Hilbert space. And I said that this is a sort of a geodesic distance that can be thought of as induced by a Riemannian metric. And the Riemannian metric is this. So if you write down, so I don't write down in this talk exactly how it looks like. There's a more or less explicit expression for this, right? But I just wanted to say that this is exactly what shows up here. And this is, so Mikhail is an expert in this. This is very interesting because it means that the gradient flow structure on the PDE corresponds to the noise structure in the STE. So in other words, if you have a PDE given, you can find different gradient flow structures for this PDE. So this means because you write the PDE dt rho is equal to a gradient of a functional, and you can have the same PDE for different choices of the functional and the gradient. And in some sense, this is a philosophical result saying that if you choose for this Stein Fokker-Planck equation that we had, this particular gradient flow structure, then it's in some sense natural, at least when you think of it. So when you think of it in terms of this noisy extension, which is again natural because it preserves this invariant measure in this, at least in this application, then sort of this statement says that they work nicely together. Yeah, and okay, the last thing that I'm going to explain is that we would like this functional to be as large as possible. So, because if this is large, let's say on one curve of probabilities rho, then it means that this expression will become small. And so the probability of deviating from the solution to the PDE is small. So this means that the mean field limit, at least hand-wavingly speaking, will be reached quickly. Okay. And in particular, we are interested in thinking about how one should choose the k, because the k, so this functional I depends on k. So first of all, it is here, but it is also implicitly here. So I didn't write this here, but as you recall, this geodesic distance depends on the reproducing kernel Hilbert space norm, and therefore on the k. And so it would be interesting to know how this depends on the k, and if one can say something. And it's in general quite difficult, of course. But what is possible is to make an expansion, so identify the leading order terms for n large and t large. It would be interesting to go beyond this. So it would be interesting to get more quantitative results in less limiting regimes. But that's what we did. So this is a little bit formal. So there is gamma convergence and contraction principle. I should also maybe denote this by different letters. So this is a large deviation functional on curves of probability measures, whereas this is a large deviation functional just on one probability measure. But you can go from one to the other by the contraction principle in large deviations. And we get this kind of term. So there's the cotangent norm associated to this formal Riemannian structure. But it's good because this is in fact understandable in terms of the function k, because it's just the it's some sort of inner product induced by the kernel k. And we can understand this a little bit. So we can say, so just in terms of notation, these are the quantities that we had here. So just to reiterate what we wanted to do, try to find condition on the kernel such that this I is as large as possible. So this I has in this regime has this expression. And now we can look at conditions on this K that in fact make sure that this is as large as possible, so as to make this mean field limit appear as quickly as possible. This is right. And okay. And so this these are the asymptotic expression for the large deviation functionals for this I. And we can see that they can be nicely, so an ordering of these I's in terms of the case can be achieved in terms of the ordering of the corresponding reproducing kernel Hilbert spaces. So we have these two kernels. We look at the corresponding reproducing kernel Hilbert spaces, which are Hilbert spaces. And then if there is an ordering of these reproducing kernel Hilbert spaces such that one is included in the other with inclusion of balls, right? So this means that the unit balls are included in each other. Then these I functionals will be ordered in the reverse order. So note that green and red here are reversed. Yeah, and this is an example. So this is an example. This is in fact a tractable thing to look at because these reproducing kernel Hilbert spaces are very well studied by now. And so we took different kernels where we knew that this inclusion holds. And so this is a good kernel, this is a bad kernel according to this characterization. And you see that somehow the distribution here is more even. I didn't put this here on the slide, but basically what this comes down to is the behavior of the kernels on the diagonal. So if the kernels are very peaked when X is close to Y, then it will have the effect that the particles are driven apart from each other. And you can see this here. And if you look at the defining equations of SVGD, you will also see this because there's this repulsion term. And yeah, you can see this effect. So in this sense, it's not surprising, maybe, but possibly this analysis will also allow us to go beyond this. Okay. Yeah, this is what I wanted to tell you today. Thank you for the attention.